All right. Welcome, everyone. Good afternoon, good evening, good morning, depending on where you're at in the world right now. I'd like to welcome you all to our 14th special geothermal talk. Today is a great topic, a very applicable topic. What we've done in the past years and the past presentations is we've covered a lot of specific topics in the geothermal world, going from theory to hydrothermal systems and super hot rock and geomechanics and all sorts of applications. And in these coming months, we have pivoted a little bit to more applicabilities with today's presentation. In a couple of months, we'll have a presentation on basically well construction in geothermal. What do we look for? Integrity issues. How do we design for longevity? We're also going to have a presentation from Rystad Energy. We're going to talk a little bit about the statistics of geothermal in Europe and across. What is going on in the world? How can we increase that 0.4% of geothermal, and how can we use the momentum to keep moving it, right? I'd like to thank you all for being here today. We are recording this session, and as per approval from our speaker, we will be sharing the slides and the recording when this is finalized. I will introduce our speaker today. I'm very glad to have today with us Ms. Virginie Schoepf. I hope I said that correctly. She's a petrophysicist with the OpenField, a senior petrophysicist with OpenField, and is a member of SPE, SPWA, and IAH.
Yeah.
She started her career with Schlumberger as a development engineer in France and later moved to a log analyst role in production petrophysics. She held the position of petrophysicist with Engie, former GDF Suez, and BP. She holds a master's degree in geophysics from École de Physique du Globe de Strasbourg. I hope I did that right. Welcome today, Virginie, and we're looking forward to your presentation. Thank you for being here.
Yeah, thank you so much, Gabriel. Thank you, everyone, for attending. So today I'm going to speak about dynamic measurement in geothermal wells using production logging zones with a multi-physics instrument. So first, I'd like to say thank you, SPE, for the opportunity to present and share. I'd like to thank also the partners, ADEME with the French National Office for Transition, Ecological Transition and Developing Green Energy, NG Solutions, CFG, SDP Logging, who were either managing the field work or on behalf of the operator or deploying the tools. And I'd like to thank also my employer, OpenField Technology. So today we're going to start first putting in context this production loggings. And I'd like also to show you present you the instrument we are using. Before we deep dive into the case study. So there are 3 different places and they are all in France. So let's put this case study in context. So they are using they are based on geothermal wells drilling that are deep wells. So there are different type of geothermal energy. There are the shallow one that is limited to 200 or 500 meters. That depend on the local legislation. That's an illustration from EJEC, by the way, the European Geothermal Energy Council. And then below 500 meters, we go into deep geothermal. And I would say there are 2 types. One that goes to moderate depths, 5-6 kilometers down to 200 degrees C. That's a geothermal that is mostly used for heating and cooling, and that's actually going to be we have example from this type of geothermy, and but there are also very deep geothermal. I think you had already different talks in this special integrals group that goes more deeper. So today, the tools we are going to use are tools that are using hydrocarbon wells also, but with the common, I would say, spec of 150 degrees C max, and 1034 bars. But of course, if we go to geothermal, that is dedicated to produce electricity, when we go about 200 degrees C centigrade, we need to have, use other type of tools. They do exist, based on flask, pressure housing. However, they don't necessarily last very long. But today, as I said, we are concentrating on this type of geothermal that is not so deep, not so hot, and on really used for heating population and offices. So we're gonna go down in the subsurface with production logging tool. So what is production logging? So here's a sketch where we have a logging truck with a winch, and we have a cable, and we are going to deploy a tool. That's the logging tool. That's production logging tool measure, of course, the depth, and you have also depth um, depth sensor to put the data on depth, which is casing collar locator or gamma ray. And on top of the depth, we're measuring pressure, temperature, and fluid velocities and fluid holdup. So, in geothermal, not mostly monophasic, at least low enthalpy, but there are some sensors that can help measuring holdups, so typically how much gas, and also inferring conductivity from the water. So what's going to, in this example today, we're going to use mostly a propeller. So a propeller, I don't know if you see me, but a propeller is a helix that is going to rotate, and it's going to rotate the fastest if the fluid flow is very fast. So the rate of rotational rate of the propeller can be directly calibrated into a fluid velocity. So let's do an example where we're going to go in an injector well. So we're injecting water in the well, and the logging tool is going to go down across the formation through three layers here. Layer A is more like a limestone. Layer B in yellow is a sandstone, and at the bottom we have some impermeable layers. And as we go down, this propeller, at first, if we are injecting, so 100% of the volume is going down, and as we're going into open hole or perforation, some of this water is going to go into the formations. So in this example, I have two permeable layers. The limestone, as you see, there is some RPS, the rotation speed of the propeller. So it starts to decrease slowly out that, and then mostly it's going to zero when it's going into the sandstone. So from that curve of the rotation, we can infer the velocity. If we have the velocity and we know the borehole size, whether because we're using bit size or better as we run a caliper also, we can deduce a rate. So the flow rate is velocity times area. And what we are doing by using the flow profile, we are trying to understand what is going in each layers of rock. So when we have the total flow profile, that is mostly proportional to the spinner RPS here, we can deduce zonal rate by simply doing the difference, and the total of this zone would be 100% of the rate. Nothing goes into the impermeable layer. So why do we need that? Especially sometime in nowadays, even geothermal wells, we tend to have maybe good static descriptions where we have more seismic, we are drilling the wells. Some area have quite a lot of penetration, like maybe Paris Basin. We can even have core analysis, fancy e-logs like NMR logging. So we have maybe a good static model, but the static model doesn't really tell you which zone of the reservoir is flowing. So even if you have some surface measurement, some rate measurement at surface, you still want to understand which each layer of a reservoir is giving you. And that we do by running a production log. In that case, in this the case study I'm going to show you, we deployed a tool that is very compact. It's just 1 meter, and in 1 meter you have pressure, temperature, inclinometry, a casing color locator to put on depth. And on this part of the tool, which is a 4-arm that opens and measure a 1D caliper, we also have array props. So they are typically on each arm we'll put a propeller, a helix, to measure flow speed. And on another one, we can put either a hold up. So typically in the oil well, we would put a fluid hold up, or also Doppler probe that can provide an alternative speed of the spinner. So this tool is very compact, it's very light. We did combine with a gamma ray and also a centralized helix, and I was just under 2 meters. So it was easy to rig up, and also to some of the reservoir can be quite have small layers, and you don't always have a lot of sump. So being compact help with the logging also. Just to mention why are they, how can we manage such a compact instrument is the instrument is using a MEMS technology. MEMS stands for micro electromechanic tools. And then you see here that's a chip that is measuring pressure and temperature. So it's really tiny. Then we integrate this chip so it gets a bit bigger. But and then we combine also other type of measurement, macro helix, that's for flow speed, optics, fluid resonator, and other hold ups, and then we can put all these different physical measurements together in order to build this tool. So just to explain the type of measurement again, so we have the main tool body with 4 arms that opens up, and on each arm there are 2 measurements. So in these case studies, there is 1 spinner in gray on each arm. The spinner are small, 11 millimeter OD, and they have a low threshold. And on the other arms, we have mixture of optical probes. So they are in sapphire, they're transparent. They can detect gas. And also we have 2 electrical probes. So this electrical probe of conductivity, that can give us directly water holdup, but also in some of the surveys, they gave us an indication of the water salinity. There are different type of flow speed measurements. So as a start, I explained the maybe most known is the micro spinner or the helix, when you have the propeller, and if you have fast flow, you're going to have a higher rotation rate. Well, there are different types. So there is a small one, the 11 millimeter OD, and a bigger one, more like 1 inch or 2.5 inch helix. And then there are also something we have been working on, the Doppler, that's using a frequency shift. That's non-contact, and there are still there's a bit of a challenge to make it work in monophasic water, because you need some heterogeneity in the flow to refract back the energy. So that's something we are working on. Today, I'm really going to show example of flow profile using the spinners. Just about the probes, the hold-up probes, I said that we are using 2 types. So conductivity probe is based on 2 active electrodes. And if there is water in contact with the 2 active electrodes, and the spacing is really small, it's around 1 millimeter, the current loop is closed and the signal will be high. That's how we detect water versus hydrocarbon. We also have measure an apparent conductivity at low salinity range. The other probe that is on the tool during this survey is the optical probe. Also, the optical probe is based on refractive index, where we are shooting light through fiber optics and thanks to a laser, and analyzing the amount of light going back to the photoelectric sensor. The first example is in Paris Basin. So that's a part of part of France map where you have Paris here, Massif Central, center of the country here, Brittany or this side, Alsace. In most of France, the geothermal gradient is around 3.5 degrees C per 100 meter, except in the Rheingraben in Alsace and also the northwest of Switzerland and Germany, where the gradient is 3 times more. That's where some of the wells, like in Soultz or Rittershofen, produce water above 200 degrees C. So today we're going to concentrate in some of the Paris Basin. Paris Basin has a very old history of drilling. So it first started with oil drilling, and that's where you have a lot of penetration. But quite early on, as early as 1962, there was a first geothermal well drilled. So it started quite well for geothermal in Paris with first exploitation of heat in Melun. And today there is almost a quarter of houses or buildings heated with geothermal in Paris. So it's not electricity, it's for heating the population, and of course we can also cool the habitation. There was a dip when in the 70s with the drop of oil and gas price that also collapsed a bit the drilling in geothermal. But the last 10 years, I think there is really a boom. So not only actually in Paris region, but certainly in France. So quite a lot of people in Paris region being heated. We estimate to, I think, 1 million inhabitants. The first case study is located in southwest Paris, of the region, in Vélizy. It's a geothermal power plant operated by ENGIE. It was low enthalpy. The target temperature of the reservoir is around 65 degrees. The investment is close to 30 million euros. There is quite a large part that is subsidized. For instance, ADEME provide a large part of subsidies. And as many geothermal plants, the life expectancy has to be 30 years minimum. So this the doublé, there is a geothermal doublé with a set of injector wells and a producer well. So there was monobore for the injector. So the injector is where we inject cold water. And then the producer here in red, that's where we get the production back. And on each well, there are three triplets. You have multilateral lengths. So you're going to have three well bore for the injector and the producer. The average angle is 60 degrees. And by doing that, there is an increase by multiplying the well bore of flow rate. The target zone is a dogger, like many of I think the geothermal wells in Paris. The dogger is high permeability sandstone. And yeah, it's open hole completed. So what the dogger, one part of the dogger has oolite. So oolite is a type of rocks where this is a thin section when you have a pellet that is deposited in a lagoon type environment, and it needs a core, which can be a grain of quartz or a grain of rock, or also bits of shell. And then during the deposition, you start to have this kind of wave in a roulis in two direction, where you start to form this round, very kind of round shape. So if this rock is not fissure, it's not very permeable, but it tends to have little fissures, and it can become very permeable. But it's not always the case. So there are a lot of work on this type of rock. I'm sharing one publication. So it's important when there are some logs being run for evaluating the formation, that not only you have just gamma ray porosity resistivity, but sometimes you go down with logs such as nuclear magnetic resonance to understand how mobile can be the fluid. Completion logs are very important. So Gabriel mentioned that there will be a talk about that in the future, about durability and probably completion log. So there are some aquifers that are used to for potable water by the Parisian, namely the Albion and the Neocomian. They are here, and they are protected by two sets of strings. That's the architecture of the well, with several strings: 30-inch, 20-inch, 13.38958, before it's completed in open hole in 8.5-inch. So very important to have very good cementation to protect the aquifers, avoid crossflow between permeable zone, and also protect the casing from corrosion. Prior the PLT, it's common to, and it was the case, to have some acid wash, and then the tool string is run down in the well. They generally start with 3 different pumping rates inside the casing, because inside the casing, that's just above the reservoir, that's where we are sure of the size of the hole. And we look at the rate, and also after that, deeper at the pressure buildup. When this step is finished, the tool is run through the reservoir up and down at different speed, and then you get the flow profile. So when we run in hole, so this is when we go from surface to the reservoir. Let me just explain. So that's the depth, that's the architecture of the well, and the reservoir is outside the casing shoe here. Cable speed, inclination, that's the well deviation, so it's going towards 60 degrees toward in the reservoir. We have spinner data, so the mnemonics for the spinner is spin. There are 4 macro spinners, small ones and a bigger one. What we see as we go down, well, there is some change of speed because of cable speed, but mostly all the spinners are rotating. Sometimes they may stop, but that's, maybe common if there is some dirt in the well, and they can get clean later. But most important, we do have several, so there is redundancy in the spinner. And then we have the water holdup map. So at surface, between surface, there is a few meters when you have actually some air pocket, some air. Then we have water. Water is blue. There are some bubbles just at the top of the water column that we can see. BC stands for bubble of air. And then this part is a Doppler. So I mentioned that we are really interested to also make the Doppler work in monophasic water. So what we see here, that the Doppler spectrum, some of the Doppler channels, that we do have some energy. However, it's quite low energy on the Doppler, because it's mostly monophasic water, and that shows us also there are not many solids or bubbles inside this column. Also looking at the running order, the conductivity data. So I mentioned that we have a conductivity probe. This probe is not calibrated to salinity compared to some of the, I think, that exists in the industry. For us, in OpenField was using this probe to really recognize water versus hydrocarbon. But there is, if in low salinity range, we know that this probe is going to be sensitive to salinity. So what we have here again is the depth, pressure, apparent density, close to 1 gram per cc. And then we have this conductivity probe data here, that's the raw apparent conductivity that is very low because we have air just below the wellhead, and then increases, then we are going to water, and we see there is a slope. There is a slope on this curve. And why do we have this slope? Actually, it could be maybe because we have a gradient of salinity, or because temperature is increasing. So we can check that if we emulate a conductivity increase just based on the temperature text, we can see that the response is very much alike the measured response. So we know that there's no gradient of salinity here. It's purely an increase of apparent conductivity because of temperature increase. What we know also from our sensor, that this increase, the fact that we can still an increase is not saturated, we know that the salinity is less than 10 grams per liter. So of course, at surface, we produce the water is produced and analyzed, and that was confirmed. I mentioned that prior going up and down, there is generally 3 steps of rates that are done at different rates. So that was acquired. So we acquire pressure, temperature, all the spinner data. And we compare a surface metering that was given to us with quite a large inaccuracy, 25%. And we, based on the data we got from the production logging tool sensors, so mostly propellers, this is inside casing, we are able to get more accurate than the surface metering. So it's more in a plus or minus 5%. So we are in good agreement with surface. Another thing that that they do at the stage, they shut in the well and they record the pressure buildup. Why do we do that? It's in order to understand the reservoir transmittivity, and that's quite key to to characterize the subsurface environment. Now, going into the reservoir in open hole, 8.5 inch, it was done in 2 different modes. First, it was done while producing. It's an artesian well. The dogger is artesian, so it's producing naturally. And we collected some data during the production PLT, just by producing. Here you have again the well architecture and the open hole part, gamma ray, Doppler, water hold up, only water, no bubbles, and then the spinner data. And we see we are not going very deep. And that's because it was difficult here to go deep. It's 60 degrees. There was no tractor, it was just with the E-line. So it was not possible to go deeper. So it was decided to take this well and inject water. So even if it's producer well, you can inject water and gather a flow profile. And that was the case in the second run. And what we see here, QW, is the flow profile across the reservoir. So what we see here, it's 100% of the flow going into the casing, and then rapidly this volume of water is swallowed by the first layers. What we know from the static data is this: we have a OLIT at the top of the dogger, and it seems that the OLIT here is very permeable and taking most of the flow. It's important to say, and I will say it again in the conclusion, that we do these PLTs in new wells just after the drilling. It's not done, to my knowledge, unless maybe there is a problem of injection or production. The operator don't tend to do again logging, obviously, because then the loop is closed and you are producing heat from the geothermal plant. So that it's possible that as we produce, we are, especially at the injector, we're going to create more maybe a natural path for the water to penetrate into the reservoir. So maybe this profile is going to be less dominated by by the top layer, and we'll get more into the deeper layers. This is another example in a different basin, actually, but still low enthalpy. The well is shallower. It's 1,000 meters. It's vertical, close to vertical, and has two types of lithology, mostly limestone and sandstone. So what we are looking, so that's directly in toward the end of the casing here, that again the reservoir the well architecture with the casing, and then it's also open hole completed, and so the yellow part here, it's in the reservoir. So what we see here, well, there's some restriction, but we have mini spinner data, the 11 millimeter. And then we have the biggest helix, that is around 2.5 inch versus half an inch. And what we see on all the spinner data, we have almost 100% of the flow. Most part of the flow is going down, and it's only when we reach the end of the reservoir that the bottom of the well, that most of the production is going into the rock. Nevertheless, if we compare the mini spinners to the big helix, we can see that there are some inflows inside the limestone. That's the limestone part. That's quite important to have sensible flow meter, because it will be able to allocate that, to say that yes, there is some that is going into the limestone. When we use, and we know that biggest helix, they tend to average more, they are more inert than the small helix. Now, if we look at the interpretation, zooming into the reservoir, so you have, as I say, we have limestone and sandstone. That's the lithology with the gamma ray. And then QZT is a flow profile while injecting. And as I was saying, most of the volumes, that zonal QZI is a zonal index, are going into the sandstone. But some of it, thanks to the small propellers, could be allocated into the limestone. So when we look at that, we see, wow, it's quite, I don't know, 300, 400 meters, well, maybe 50 meters of sandstone, and that's a vertical well, and we are drilling a lot, and with most of the flow going to sandstone. So that can be, again, maybe trigger some question on maybe should we do in the future deviated a longer stretch into a longer part into the sandstone. Well, yes and no. Again, the limestone, this is a profile just at the start. It may be better may have more fluid going into the limestone, but there is also the fact that this well managed to get quite the objective in terms of rate. The last example is also in a urban area. What is interesting here is that we can show you the data from the injector and the producer. Again, there was a PLT was done in order to record some station at different rates and the PBU, pressure buildup. And after, the PLT tool string was run in the injector well and in the producer well, while in both cases water was injected. So we are recording an injection profile in both wells, even if there is a producer. And again, the temperature is quite low, is close to 60 degrees. The distance between the two wells at the two is over 1 kilometer. First, again, just to show you a bit some spinner calibration. So I didn't mention that, but how do we do spinner calibration? We acquire data at different cable speed. LSPD is cable speed. So you move the tool at different speed, and then you record the rotation per second of the different spinner. From that, you can do some. One way is to do some cross cross plot where you have the RPS, rotation per second, and cable speed, and then you will get a slope if you are in stable condition, and that slope is going to be the conversion RPS into flow speed. So we can do that for all the spinners. So the mini spinners that tend to have same standard slope. And then the inline spinner, remember there is a bigger helix, give us also a speed. So what's interesting here, if we look at the type of flow, we have the flow rate was 75 meter cube per hour, and inside the casing it's 8.6 inch. And if you, what we could see, we were quite very accurate velocities, good calibration plots. We can, and several macro spinner which repeat velocity around 30 meter per minute. Whereas the spinner at the center, the biggest helix at the center, is reading higher. So why is that? Well, if you use the flow rate and the ID of the pipe, you can see that you are actually in laminar flow. And laminar flow, actually, depending on where you are in the cross section, you will get different velocity. So the helix, the inline spinner, is at the center. So reading higher velocities than the mini spinners that are just less than 1 inch towards the wall. Now if we look at this flow profile, we calculate the flow profile in the injection well, in the producing well. They are around 800 meters away at the top of the reservoir. And what we see here, so with depth, gamma ray, velocity, flow profile, and then in the other well, we acquire the same data, and we see that actually there is quite good conformity of the flow profile. Except this well, there seems to be more going into this sand, but overall good continuity that would suggest a lateral continuity. But what we're told also by the operator is that there was actually not the same salinity produced in the two wells. So, but in terms of layers and at least permeability, the two wells look similar. Before concluding, I just wanted to give some count, discuss a bit the spinner. So we show quite all these studies. We rely on the macro spinner to calculate the rate, but we do also acquire temperature and the Doppler. So on temperature, it's very important measurement, temperature, especially if you have flow behind pipe, cased and perforated completion, and fracture reservoir. So and we do have also temperature, acquired temperature. So it's always a good exercise to either do a forward modeling with the temperature you have or invert the temperature. So for instance, let's look at a case where we have here depths, 2 perforations, and then this is a temperature response when you have pumping around 35 degrees C temperature, and then you have a decrease of temperature, and then going back to high temperature, 90 degrees. That's quite deep well. So what we see from the temperature, a lot of cooling at the top perf and top of the second perf. If we use the spinner, let's say we use the spinner only, which is spinner as a response, like everything is going into the first perforation, a little bit bottom. If we use the spinner and as a main input, then my theoretical temperature would look like that, with a big the big bump. It will take a lot of time to warm back. Look at the warm back, where you inject most water. That's when it stays blue, it means a cool temperature. And where you are not injecting so much, it's going to heat up more quickly. So actually what we see, if we were using the spinner here as the main input, we can't find again the response of the temperature that was really measured. Now if we use the temperature as input and you do forward modeling or inversion, you have another flow profile, that's the flow profile you would obtain with the temperature, which look more reasonable. You know that it's with what we know from the geology, that is more I would say gradual profile than this, using only the spinner. So, and there are tools that exist on different simulator always that you can do that. Another thing that is nice to do, if you can do it, is to do warm back analysis when we have or cool back temperature with the temperature and you look, you pump, you stop pumping, and you record while shutting the variation of temperature. So where the formation takes the most is going to take the longest time to go back to normal. Well, another measurement we would like to develop in geothermal wells is the use of Doppler. So Doppler is a measurement that is contactless, where you're using in our case, ultrasonic energy that we are emitting through a Doppler probe, and that wavefront is reacting with any heterogeneity in the wellbore. Can be sand grain or bubbles, and that bubble or sand grain will diffract back the energy towards the probe that is also a receiver. And by analyzing the different frequency shift between what you send and what you emit, what you get back, you can deduce the relative speed of this heterogeneity. So if the heterogeneity they flow at the same speed as the main fluid, then you get a relative speed of water. So that works well in multi-phase because bubbles of other fluids create strong signal, but we are working to make it also work in monophasic water. So in conclusion, today we wanted to show how production logging can inform about the heterogeneity in the reservoir. So what is generally as a general conclusion is often the operator got surprised by the flow profile. It's not always easy to predict based on static data. And it's important and they are integrated this dynamic well result into reservoir models. That part of the work, I think in France, is done by the BRGM, which is the Bureau de Recherche Géologie Minière. On top of that, now, looking at the reservoir model, they also look always at the production of cooling bubbles, because of course by injecting water a long time, cold water a long time, you're going to create a cool bubble that you don't want to come too fast to the producer, or also to interfere with neighboring geothermal doublet. In the case study we show, it's always a flow profile in newly drilled well. So there's a baseline production logging. After that, no, unless you have major problem with the injection of the production, you will not run a PLT. So that can be also a view at a certain time of the flow profile that is going to evolve with time. So what we hope we trigger also in the discussion after is, if you are involved with geothermal wells, how often in your area do you run this tool? What are the limits? And yeah, if you have any feedback, that would be great. So I'd like to thank you for your attention and leave the floor to questions.
Thank you very much, Virginie. That was a great presentation. A lot of detail, very applicable. So that's very, it's very useful. We're trying to learn these kind of things. And looking at the chat box, we have a couple of questions that I'm going to address. So Ivan Virshlo says, is it true that the Rhine-Graben geothermal gradient is 100 degrees per kilometer? Basically 200 degree on 2 kilometer depth. Do you have any
Yeah, it's
insight on that?
10 degrees per kilometer. For 10 degrees, it's 3 times more. I'm mixing with the units. It's 10 degrees per 100. Yeah, it's 100 degrees per kilometer. Is that was the question?
Okay. Yeah.
But there are some areas that even slightly higher gradient. Maybe there are people from Germany or from Alsace in the call, ES or I don't know, Lithium de France or people from yeah, that are it's one 100 degree per kilometer, but even slightly higher sometimes.
Yeah, we do see those. Not even not just in Europe. Earlier we were talking about it. The projects in the United States, there's some areas where it's easy to find 100 degree per kilometer. So
Yeah. Tuscany, bon, Hawaii, bon, there are lots of California.
yeah,
There are
Oregon.
Yellowstone. There are lots of
Mhm.
Indonesia. There are, yeah.
That's maybe something to think of as for the future. We're gonna have to design. We talked about it, tools that can handle super hot
Yeah.
environments. That's something for the future. Thank you for that. And then we have Mr. Thomas Franzen that says, "Dear Virginie, merci for your comprehensive presentation. Ask
Thank you.
about the first three. May I ask about the first three PLT static stages measured within the casing while
Yeah.
injecting or producing?"
Yeah, that's something discussed with people from CFG. Bon, there are all three of them are French example. Huh? This is something common practice to do. So generally, first also you do an acid wash because in Paris Basin you have the limestone rocks, and it's a step they do uh, three type of flow rates in order to do a well test analysis. They are followed by a PBU, and then it goes into a reservoir engineer interpreting the PBU, and that is a response to the multi-rate test. So it's to find the boundary, I guess any boundary that you would not have seen with seismic, because also in Paris Basin they're using seismic data. You don't want a fault between the producer and the injector. I didn't do interpretation of well test on this case study, but if there are more detailed question, I'm happy to ask the partners.
So he was asking, is it while injecting or producing? I'm
Sorry, while
assuming.
injecting,
Yeah,
right.
while injecting.
So
Okay. And connected to that, thanks for that question.
it can be
Just
also while
wondering.
producing, but it depends on the well, actually. But yeah.
But how do you designate the flow rates that you will test at? I suppose it's very well specific. And then when you said you're looking at the boundaries, is that what later would define what the distances in a doubler would be injector to producer? Because earlier I saw 1,400 meters. Obviously, you have to look at what the subsurface setting is. But based on your experience, the decision on the rates and then what you get
Yeah,
out of the PBU.
generally the wells are the injector and the producer are already drilled more or less at the same time. Again, I may if some operators are here, they may scratch their head, but from what we saw is often the injector and the producer are already drilled back to back. So there
Mhm.
is not a lot of change that you can do to the spacing. But I think this basin is relatively well known in Paris Basin because you have
Okay.
every sometimes 10 kilometers or 5 kilometers at the moment there are some, so maybe 6 kilometers you have some drilling. So they don't tend to change then exactly the rate. Often the target, what I see in Paris Basin on the technical data that is sent is that you the delivery rate is around 300, 400 meter cube per hour in order to make this economical
Yeah.
for a town around 10,000 people, and it has to last 30 years. And then there is some things that you want to check with the transmittivity is that you are not going to have a decrease, I think, of 0.5 degrees C at the injector after, you know, like 30 years would be the duration of the plant.
Mm-hmm. All right, thank you for that. There was a question that came from Carson Ball. Said, can you repeat why the PLT measurement does not work so well in fractured reservoirs?
No, and I wouldn't say the PLT, again, PLT is a production logging, and production logging, the best you do is you have all type of sensor, because then you can analyze the data with anything you want. I have heard sometimes people, especially in granite, when you have fracture is dominated by fracture, they don't trust the spinners, even in open hole, because they say sometimes spinner get blocked. Um, and then anyways, they don't like the spinners, so they don't run spinners, and they just rely on temperature more. I would say if you have and most of the vendor have a tool string that contain not only temperature, but you can put a spinner, and they get quite close. So the problem with the propellers is, well, they can be blocked if you have dirt in the well. Sometimes they don't rotate because the flow is too low. But secondly, there is a case also if you have completed cemented and perforated, that you can have flow behind pipe, because maybe you don't have good cement, or if you are in a sand screen, you don't have propellant everywhere, and then you can have what we call flow behind pipe. That's, for instance, a cemented completion where you have perforation. The triangle in blue are perforation, but it's cemented. And what's going on in this well is actually most of the spinner data is real, is most of the fluid is entering here, but maybe there is also and then there is no cement, so we can see, because we compare spinner to the temperature measurement, that is much more telling you that the flow intake is distributed over several meters, when the spinner said, well, 50% of the flow is going through at one depth. And that's most likely here in this well, even if they told you cement plug, it looks good, cement is good, is this well has flow behind pipe, and even between two perforation, we can see the temperature intake, the temperature profile looks like also you have flow, between the two perf. And thanks to temperature, you can actually recalculate the flow profile. So I wouldn't say spinner are bad. Let's say sometimes they don't rotate well, or you have to be careful if you are in a case and perforated completion or gravel pack with not propellant everywhere. You can have some flow behind the inner string, because the spinner, of course, they are inside the casing or the inner string. They can only see where they are, where the temperature is sensitive to to the heat, to the temperature of the rocks across the casing. I
All
don't know
right.
if I answer the question, but
If I don't get any text in the chat box, we will assume that Carson is happy with the answer. A question, I was wondering one thing. So you're involved in this kind of work. Do you generally have like a continuous quotes monitoring program with whichever customers you have, or it's kind of a one time you go out there? How does that dynamics work
yeah.
in the sense of
So,
understanding?
bon, for us, actually, in that case, it was mostly SDP logging. That is one of the author. So there's a company in France. The mother company is SMP, a drilling company. So they are drilling and they are acquiring the log. And SDP has used a more open field instrument. So it's really SDP that is on site. And then together with the likes of Engie, if they are a maître d'œuvre or CFG, company like that, or also Antea in France, they will execute or witness the logging program. And the program are like, I would say, for oil and gas, they are decided in advance. And there are people like oil and gas, and there are same organization on shift, because they are drilling and logging, 24 hours, 7 days a week. they are in urban areas, so they need to make also careful with the noise, but there will be some noise, but they are working around the clock. And it's not because it's geothermal and you are in cities that people are organized, very organized. And so to answer your question, it's really on the logging part, SDP logging in these cases. But we, work or help if they have question on sensor, but it's a teamwork.
Understood. Thank you. We do have a last question, is a bit general, but from Ravi said, yeah.
Sorry to ask you, a colleague remind me that they were on site, some OpenField at the start to introduce the new tool. So then we can go also on site, but in the main business is SDP logging.
Okay. Thank you. So Ravi says he's got a general question. How do we get temperature versus depth data from an open source platform? It's a good question. Are you aware of any open source platform of temperature and data for Europe? He's working on his research proposal.
Well, there is a GeoBase in France, and there are also in the Netherlands, and Netherlands has a good database, so I say it depends. But for the French, there is going the Geo database, I think, from the BRGM. And normally, so I don't know if you are that's this link I can send the Geo database BRGM. Maybe I can email you, Gabriel, and you can forward after. So there are, and the thing I look at it because I look at the report pre-drilling, post-drilling. There are lots of interesting reports about the there was a Virginie Ram and other that do reports. They look at the data. The BRGM is actually doing the synthetic regional synthesis of this data. So after it goes back to the Bureau de Recherche Géologique et Minière is a bit like the how do you call it in the US, UGS in the US, or they are doing the regional synthesis. So you will find it's a public database. So I don't know if you are not in France if it works or not, but let's test it. And in the Netherlands there is also a good database, probably in Germany too, but they tend to be more public to stimulate geothermy. It's, I think, very important. A good question.
Yeah. So if you don't mind including that link, it would be great. I also posted one that's for the US. Stanford just created a thermal model. There's Mr. Franson sent us a link. Nice. That's a great. Thank you very much. I'm gonna save this link too. Afternoon work. Great. So we've answered all the questions. I would like to say one thing. I did see someone ask for the PowerPoint. We will not be sharing the PowerPoint. We will be sharing the PDF version of the slides, and also the recording. So expect an email in the coming days. And then that essentially would wrap up today's session. I'd like to thank you, Virginie, for your time. You've been very supportive. Thanks for sharing your knowledge. Please keep an eye out. We're going to do a lot of these things in the upcoming future. Obviously, I think in the summertime, we might take a short break because everyone is not going to be on vacation. But we have some great talks coming up. From technical to Rystad to well integrity to basically looking at geothermal reserves and how do you quantify those? What is the approach? So follow us, and thank you everyone again.
Thank you very much. It was great, and I look forward to participate to other as someone to attend the presentation. I know you mentioned Naomi last time that I miss, but you have also a YouTube channel, I think.
Yes, absolutely.
So where people can look back at the recording. So that's great.
Yeah, I will share that in the email when I send it out.
Yeah. Thank you.
Thank you.